Greetings from EPG Pathshala. Today we are going to check the module DES algorithm. DES stands for Data Encryption Standard. It is the symmetric algorithm. Symmetric algorithm means the sender and receiver both use the same key to encrypt and decrypt. DES works with 64-bit input. It has a 56-bit length of key, and the output of the algorithm, that is after encryption, we will get the string of 64 bits. How DES algorithm works, how many rounds we have to go through, and what is the strength of DES algorithm, that we are going to check in the discussion. So first I would start with when DES algorithm was issued. DES algorithm was issued in 1977 by National Bureau of Standards, which is now National Institute of Standards and Technology. As I said in my introduction, data is encrypted in the block of 64 bits. The key length is 56 bits. The output is 64 bits. For decryption, the same keys are used. In DES, we are going to use 16 rounds. So 16 keys are used. It will go from K1 to K16. When we are doing decryption, we will be using the same keys but in the reverse order. Means K16 first and K1 last. This is the block diagram of DES encryption. You can see the 64-bit plain text is input. Initial permutation is followed. Permutation and substitution. Two keywords are discussed when we talk about encryption or cryptography. Substitution says we are substituting one character for another. Permutation says we are changing the position of the character. Here it is permutation, so we are changing the bit positions. So whatever plain text we have got, we will change the position of the bits. Then round 1 is performed, round 2 up to round 16. In each round, 60 key is fed. Key goes like this, 64-bit key is input. It also goes to the permuted choice. Then it goes to the left circular shift, then permutation again, and then it is ready to be inputted to the round 1 plain text. We will see in the detail how the key generation algorithm works, but just to put a point, initially when we want to generate key, it is 64-bit input. From that we are extracting 56 bits. Then after performing left circular shift, we are permuting it and we are taking 48 bits. This continues for 16 rounds. The same process continues for the 16 rounds. Then whatever output at the end of the 16 rounds would be swapped, and at the end inverse initial permutation, means the first step was the permutation. Now the last step is also permutation, but the last permutation is the inverse of the initial permutation. So at the end, the output would be the 64-bit ciphertext. Just to give you an overview of the DES encryption algorithm, 64-bit plain text passes through the initial permutations. Input bits are rearranged in the permutation. Then 16 rounds are performed with the same function involving permutation and substitution. The output is of 64-bit. The left and right halves are swapped. Means the 64-bit output would be divided into 32 bits input. The left part and right part, they would be swapped. The swapped output is passed to the inverse permutation, and that is inverse of initial permutation as we discussed. We want to check how key generation is done. So 56-bit key is used. The key is passed through a permutation function. For each of the 16 rounds, a sub key is produced. We will call it K1, K2, K3, K16. We will denote it by suffix Ki. I denotes the round number. From the block diagram, it is clear that combination of a left circular shift and a permutation creates the 16 keys. And for each round, we are using different sub key. DES works on binary numbers, zeros and ones. Each group of 4 bits makes up hexadecimal or base 16 number. Binary 1000 is equal to hexadecimal number 6. If I want to represent 1111 in hexadecimal, it is represented by F. DES works by encrypting groups of 64 message bits. That means 16 hexadecimal digits. Example is on the screen. Plain text is given 02468A CE EC A86420. Key passed is 0F1571C 947 D9 E859. The ciphertext generated is DA02 CE3A 89 EC AC3B. But what is and how the process goes, that we are going to see in the detail. M is the plain text message. Let M be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. This time we have represented M in the hexadecimal. What I said, DES works on bit. So we would be converting them into bits. So representing M in the binary format. So first 0 would be represented by 0000. Last F would be represented by 1111. Since M is 64-bit long, we would be dividing them into 32-bit halves, L and R. 64-bit input, we want 56 bits out of this 64-bit input, so we need to discard 8 bits. Which 8 bits we are going to discard? We are going to discard bit numbers 8, 16, 24, 32, 40, 48, 56, 64. All in the gap of 8, the bits would be discarded. Now we are given the key K, that is 133457799 BB CD FF1. Once again, let me remind you, bit DES algorithm works on bits, so convert this key into bit binary from hexadecimal. DES algorithm steps are clear. Step 1 is create 16 subkeys, each of which is 48-bit long, and step 2 is encode each 64-bit block of data. So first step is create 16 subkeys. We already have seen we have an input of 64-bit. Permutation is performed according to the PC1. So PC1 is well defined by the developers of DES algorithm. So you can see on the screen what kind of permutation you have to follow. 57th bit becomes the first bit, and 36 and the fourth bit becomes the last bit. Permutation table is given to you. Now from the 64-bit key we get 56-bit permutations. We have already discarded 8 bits, saying that 8, 16, multiple of 8, in the gap of 8, all bits are already discarded. We have performed initial permutations. So now we are with the 56-bit key. Split the keys into left and right halves, C0 and D0. Each half would constitute of 28 bits. Perform the permuted key, we will get C0 and D0. We have to generate 16 subkeys. So we have to generate 16 blocks. We will denote them by C0, D0, C1, D1, C2, D2, so on. We will call them in general Cn and Dn. No wonder now you know n is between 1 and 16. Each pair of blocks Cn and Dn is formed from the previous pair. We will denote previous pair by Cn minus 1 and Dn minus 1. N goes from 1 to up to 16. What is the formula of generating the round keys? We need to perform left circular shifts. For example, if we are given C0 and D0, and if we want to perform, or if we want to get C1 and D1, we have to perform one left circular shift. So shift all the bits 1, it's a left circular shift. So what would happen? The bits would be shifted to the left, and the most significant bit would be circularly shift, and it will take the position of least significant bit. The same way, if you want to generate C2 and D2 from C1 and D1, once again you have to perform left shift of 1. From the table you can determine if you want to generate C3 and D3, they are obtained from C2 and D2, and the left shift you have to perform is 2 times left shift. Now you can check all by yourself. If you want to generate C16 and D16, it has to be generated from C15 and D15. How many left shifts are to be performed? 1. One left circular shift need to be performed. So now from initial C0 and D0, we are ready with C1, D1, C2, D2, C3, D3, C4, C5, so on up to C16 and D16. For 1 less than or equal to n less than or 16, apply the following permutation table to each of the concatenated pairs Cn and Dn. Each pair has 56 bits, so apply permutation table 2 to get only 48 bits. From the table you can verify the 14th bit would become the first bit, and 32nd bit would become the 48th bit. Going ahead, now we have first key, that is C0 and D0. We applied permutation and we got K1, that is 48 bits long. Whole process is clear to you. Initially 64 bit, we discarded bits, we got 56 bits, we applied left circular shift, then we applied permutation, and finally we are with the key of length 48 bits. So same way after permutation on C0, D0 to C16, D16, we are with K1, K2, K3 and K16. Remember, our key length is 48 bits. Our input was of 64 bits. After rearranging the 64 bit, this was all discussion about key. Now we are back to the discussion of input of a plain text. The block diagram said plain text should have an initial permutation that rearranges the bits, and you have it in mind, the 58th bit of plain text becomes the first bit and 7th bit becomes the last bit. Now I have given you the example that what was M, and after initial permutation what you get. Once again we will divide our input into two halves, L0 and R0. L0 would be of 32 bits, R0 would be of 32 bits. We have to go through 16 iterations DES works with 16 rounds. A function f which operates on two blocks, one would be the data block and one would be the key block. The data block we have divided into 32 bits. So L0 of 32 bits and R0 of 32 bits. We have key of 48 bits. So we would be operating on L0 differently and R0 differently. We are going to use XOR operation, and in my slide I have denoted them by plus sign. The formula for generating Ln and Rn is we have to generate the new left and right from the previous left and right. So if I want to generate Ln, I will copy the right which is denoted by R and R of the previous round, that is Rn minus 1. And if we want to generate right half of the next round, we would be taking into consideration the left half of the previous round, plus we will be applying the function on the right half and the key of right half and left half for the current round should be used is the previous ones. This results in the final block for n equal to 16 of L16 and R16. So for example, for n equal to 1, we have K1, we have L1 and we have R1. So to generate L1, we need to copy R0, and to generate R1, we need to take L0, apply the exclusive OR with function. What are the inputs to the function? R0 and K1. Now, how does the function f works? To calculate f, first expand each block of the Rn minus 1 from 32 bits to 48 bits. Why to do so? Because our key is of 48 bits and right half which we have generated is of 32 bits. So exclusive OR cannot be performed with 32 bits and 48 bits. So we need to expand this 32 bit right half to 48 bits. How will we do that? We would be repeating some bits of the right half to generate the 48 bit block. For that we are given a selection table. We will call it expansion table, which will generate 48 bits out of 32 bits. So you can see the expansion table or selection table in which we have repeated some bits. So first, in the first row you can see 1, 2, 3, 4. Before 1 we have appended the bit number 32 and after 4 we have appended the bit number 5. Second row you can check in the middle, it is 5, 6, 7, 8. Before 5 we have appended 4th bit and after 8 we have appended the 9th bit. Now, so in such a way, by repeating the bits, we have generated 48 bits output out of 32 bits. Remember where we are. We were working on generating L1 and R1 from L0 and R0. Now we have expanded R0 into 48 bits. We have to apply the function. Function is nothing but exclusive ORing the output of the expanded right half with the key. So key would be of the current round, and for the expansion the right half which we have used is of previous round. So it would be said Kn plus Rn minus 1. To work around with generating R1, what we are doing? We are doing L1 plus applying exclusive OR with K1 and expanded R0. So a function would generate 48 bits Now 48 bits. Now remember, the catch is we want to perform exclusive OR with L1 and the output of the function, that is exclusive OR of key and R0. Now L0 is of 32 bits and output of the function was 48 bits. So once again we have to convert this 48 bits into 32 bits so that the exclusive OR operation with left half can be performed to generate the right half of the current round. For the 48 bit, we would divide them into the group of 6 bits. We will call them S boxes. Each group would contain 6 bits. For each 6 bits, we have a different S box. Located at that address will be a 4-bit number. The 4-bit number will replace the original 6 bits. So S box would convert the 6-bit input into 4 bits. The net result would be 8 subgroups of 6 bits would be transmitted into 8 groups of 4 bits. So 48 bit we would write in the form of B1, B2, B3, B4, B8. Each BI is a group of 6 bits. We would be applying the substitution function. 8 substitution boxes, so S1 B1, S2 B2, S3 B3, S4 B4, S5 B5, S6 B6, S7 B7, S8 B8. In general, we would be denoting SI with input BI, that refers to the ith S box. Keep in mind, each S box takes 6-bit input and generates 4-bit output. How would it be done? So we are given 6 bits. So take a first and last bit that represents a decimal number in the range of 0 to 3. So if the first bit is 0, 0 and last bit is 0, it represents 0. If the first bit is 1 and the last bit is 1, it represents 3. The middle 4 bits of B represent in base 2 a number in the decimal range 0 to 15. That means if those 4 bits are 0, 0, 0, 0, they represents decimal 0. If those bits are 1, 1, 1, 1, they represents the decimal number 15. Look up the S box table, the number in the ith row and jth column. What I said, let me repeat for you. Let's take a first bit and last bit of the 16-bit input of the S box, and that represents a row, and middle 4 bits that represents the column number. So when you look at the S box, find out a particular row and column according to the input you have received. For example, the input to the block B is 0, 1, 1, 0, 1, 1. Take the first bit 0, the last bit 1, it gives you 0, 1. So this represents row number 1. The middle 4 bits are 1, 1, 0, 1. So they are equivalent to 13. So look at the column number 13. So now you, in the S box, you have to look into the row number 1 and column number 13, which appears to be 5. So your output of the S box is 5, which is binary equivalent to 0, 1, 0, 1. We can say S1, that is S box 1, with the input 0, 1, 1, 0, 1, 1 gives you the output 0, 1, 0, 1. For your reference, I have kept S1. You can check, it represents the rows from 0, 0 to 1, 1, and it represents the columns from 0, 0, 0, 0 to 1, 1, 1, 1. You can check the entry, as I said, first row and 13th column, it represents 5. In such a way, you can look at the S box S2, look at the S box S3, look at the S box S4, S5, S6, S7 and S8. Now, what we observed at the for the first round, we obtained the output of the 8 S boxes, and the final stage in the calculation of F is to do a permutation P of the S box output to obtain the final value of F. So whatever is the output of S boxes, we need to again perform the permutation. Once again, the permutation table is on the screen. The 16th bit would become the first bit and 25th bit would become the last bit. So the permutation P is a 32-bit output from a 32-bit input, and what we have performed is a permutation. So this is what you can observe after permutation. The output is like this. And in the next round, the same way we have to perform L2, which is equal to R1, and then we have to calculate R2, which is nothing but L1 exclusive OR with a function output. That function works on R1 and K2. Repeat them for the 16 rounds. At the end of the 16 round, we will have L16 and R16. Reverse the order of the block. That means take the R16 first and then L16. What is left to be done? Final inverse permutation. So that table is again on the board. What you have to do is the 40th bit becomes the first bit and 25th bit becomes the last bit. So this is the final permutation which we have to perform. So now process all blocks according to the method which I have explained. Reverse the order of the block, and what you get is the final hexadecimal format output. So you can find out, we started with M, which was 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, and we ended up with a ciphertext that is 85E813540F0 AB405. Decryption is simply the inverse of encryption, following the same steps, but all steps need to be followed in the reverse order. What is the strength of DES algorithm? DES algorithms use 56-bit keys. That means if anyone wants to apply brute force attack, the attacker has to try 2⁵56 possible keys, which is impractical. The nature of DES algorithm, design criteria of S boxes are not made public. No one has been able to find out the weakness in S boxes. Talking about timing attack exploits that encryption and decryption algorithm takes slightly different amounts of time on different inputs. So to summarize my module, what we have seen is DES algorithm is a complex algorithm to generate a key for the 16 rounds. Then we have to pass through each round. We have to use the S boxes, and after S boxes again perform the permutation, last permutation, and at the end we also checked that what is the strength of DES algorithm. Thank you.